There we go. I got onto this other screen before it started, and I'm going to hide. All right. So section 11.1 in your textbook is about sequences. And I've avoided using the word sequence because our main push is the issue with series. A sequence is when it's just a list with commas in between the numbers. And I'm going to need to be able to talk about a sequence of numbers as well as a series. The series is when the numbers are added together. So sequence, commas, series, addition, signs in between, or subtraction, But make sure you understand the difference between those two words, and I'm going to do my best to not accidentally use them in place of the other. Now, you need to know notation. If you see these brackets, let me get that out of the way. If you see brackets, that's referring to a sequence. When a sub n is used, and I'm going to also tell you that as we go throughout this unit, you're going to see sometimes b sub n or c sub n as we talk about particular sequences. But we're primarily going to see them inside of a sigma. So if you see these same formulas in a sigma, that's automatically referring you to the series of those terms. But you need to understand when these are being used, it's referring to the formula of the individual terms of the series. So make sure to clarify, these are formulas for individual terms of the series. And to make sure you're clear, when I say term, I mean something that is in between an addition or a subtraction. Each of these are terms. Now, some words that you do need to be familiarized with. An increasing sequence means, well, the terms are increasing, kind of straightforward. If you are told it is decreasing, then the numbers are getting smaller, 5, 4, 3, 2, 1, 0, -1, -2, -3, that kind of thing. Note that if you see the word monotonic is referring to either increasing or decreasing without specifying which one, because that is important. It's going to be very important to know if the numbers are all getting bigger, 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 or smaller, 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 or are they going all over the place? Know that the AP test will often use the word strictly in front of these words to make sure to clarify that you are not dealing with an or equal to. So if you see the word strictly increasing or strictly decreasing or strictly monotonic, they mean that it is for sure always the next one is bigger or the next one is smaller. Okay. And that's all I'm going to say from section 11.1. However, I will be at times bringing up things that are in that section. But I have learned to be careful about not spending too much time on sequences because our primary objective is to actually add them together. So, with that said, I now need to bring up partial sums. So we are now in section 11.2. Make sure you can see that nicely. A partial sum is when you are dealing with an infinite series, but you chop it off. So it's a partial sum of the infinite series. And know that the sub number that you see on an S, and I want to make sure you understand, S will never be used as the name of a sequence. So if I come back up here to where I was saying that A sub n is the most common letter used for the formula of the individual terms. Sometimes B gets used quite a bit, a little bit less. We need to throw in C. S sub n will never be used for a formula for a sequence because it is reserved for a partial sum, which is very, very, very different. When you look at that A sub n, it is the last term that is being added to a list of numbers being added to create a partial sum. So make sure you're very, very clear about that difference. That particular difference ends up confusing people sometimes. So nth partial sum, where was I going? Yeah, it's cutting it off at a particular, it's not going to infinity. Now, some important words that you have seen before. Convergent and divergent. And you're going to be so familiar with these two words. So familiar. Now, here's the thing. This is referring to the sequence of partial sums. The sequence of the partial sums. So when you are looking at this, it's referring to the list of the sum of the first one terms, comma, the sum of the first two terms, comma, the sum of the first three terms. Up to a particular n that we decide to cut it off on. And I want to make sure to clarify. That means you are literally looking at and so on. And it's really important right now to make sure you understand the two distinct differences because they are huge. Now, if you are, for some reason, able to have a formula for the nth partial sum, you are able to then look at the limit of that sequence. If there is an answer to the limit as n approaches infinity of the nth partial sum, that is the infinite sum. So know that when the letter S is written by itself, that is referring to the infinite sum. But if a subnumber is written on that S, then it is a partial sum. Now, if that limit exists and it is a real number, it wouldn't exist if it wasn't a real number, then we call that infinite series convergent. And then you can see here, when you have the plus ... after the formula, you are referring to it as an infinite series. If you do not put the plus ... and this is all you write, then you are referring to the nth partial sum. If you find out that this limit of the partial sums does not exist, if that limit does not exist, then your infinite series is divergent, and it just doesn't have an answer. So convergent and divergent is about whether there is an answer to the limit as n approaches infinity of, very important, the nth partial sums, not the formula for the individual terms, because that's a whole different ballgame. You are convergent with your infinite series if there's an answer to the limit of the nth partial sums. All right. And that was it for what I'm considering the introduction of sequences and series. What's the difference? What's the terminology? And now we're going to start on to, yay, geometric series. Geometric series, super important series. Extremely important series. And it is something that you did back in Math 1 or Math 1 Honors. You did a little bit with sequences and series, and you looked at geometric series. And they kind of used geometric series to introduce you to the exponential function. The difference, actually, how about I just show you what I drew in the last class so I don't have to redraw it. Haha. So here's the difference. If you're looking at the function y equals 2 to the x, an exponential function, it has a domain of all real numbers. Its domain is all real numbers. And it is a continuous graph. When you have a geometric series, the terms that are then adding, so right now this is just the terms that are about to be added together. Those terms, oopsies, use that color. So the first term, a sub 1, is some number. Then the second term, a sub 2, we are looking at, actually no, that's looking at it only as a sequence. Okay, you're not listening to me. Okay, if I'm looking at the sequence of terms in a geometric series, then I am looking at, if the base is a 2, then it is a discrete function because it is not dealing with continuous, it's dealing with following the natural numbers. These numbers are just telling you the position in the sequence, and then when you follow these y values, they are the formula of an individual term in the geometric series. If you are dealing with an exponential decay model versus exponential growth. So you get exponential growth when the base of your exponential is greater than 1. You get a decay model when your base is between 0 and 1. With a decay model, you can see that the individual terms are actually getting smaller and smaller and smaller very, very quickly. If you were given a series where you have some starting number, whatever it may be, and you are multiplying by 2 to the power of n, do you see that there is no way that thing is going to converge? It's kind of a joke to even think about it, because the terms you're adding together are blowing up. The more terms you add, you're adding larger and larger massive quantities to the sum that is already large. And we're going to see in a couple of different ways. But this is one way to look at the issue of if my common ratio, the common ratio in a geometric series is the number you multiply by to get to the next term. So if my first term is 6 and my ratio is 2, then my next number is 12, 24, 48, and I keep going. You can see through common sense that if your ratio is larger than 1, that infinite series is not going to converge. It's heading to infinity. If you have the decay model, when I look at it as a continuous function with a base that is between 0 and 1, with a domain of all real numbers, I can see this asymptoting happening. Asymptoting does not mean that when I add all these a sub numbers together, that I'm going to get an answer. But it sure does make it something to look at. You're going to have to learn that you cannot trust your eyes with whether a sequence is going to create an infinite series that converges or diverges. You have to do the math. Because you're going to find that there are a variety of series that, if you looked at them term by term, are asymptoting to 0. In fact, we're going to find out that that's the first thing you're going to look for, because otherwise it's wasting your time. If the terms themselves are not heading to 0, you can't add sizable numbers forever and get a real number. You have to be adding numbers that are shrinking toward 0 forever to even consider whether the sum of all of them could be finite versus infinite. Now, with the geometric series, I'm not going to say right away that a ratio of 1/2 will converge versus diverge. We're not there yet. And we're going to come to a full conclusion on Monday. For now, I'm going to show you something really fun. A geometric series will do the following, and it's awesome. Okay, are you ready? Yeah, get comfortable. So, we are going to come up with an actual formula for the nth partial sum of a geometric series. with an understanding that whatever number A is, that is the first term. Oh, first, try a little bit better there. First term, and the R is the common ratio. So the R is the number that you multiply to get to your next term. We are going to come up with a formula for the nth partial sum. And we may not have time today, but eventually we're going to ask, okay, once we get a formula, is there an answer to the limit as n approaches infinity of that formula? And if there's a real number answer, then we've got to converge. If it's heading to infinity, we've got to diverge. Okay, now my alarms are based on not what today's schedule is, so I need to remind myself of today's schedule. 12:50. Cool. We have until 12:50. All right. If you want to do the math on paper, or maybe you just want to sit back and watch, whichever, know that you are starting with this line, that we're going to be looking at the nth partial sum. If I add together the first n terms, this is understood to be for n equals 1, this is n equals 2, this is n equals 3, and this is the nth term in its entirety. And it stops. Now, you're going to take this equation and you are going to multiply both sides of this equation by r. On the left side of the equation, multiplication by r means I have r times s sub n. On the right side of the equation, I need to distribute my r over the addition. So that means I have that the first term of this series is a times r. The second term of this series is a times r squared. And then a times r cubed. Oh, too many dots. It's only supposed to be 3. There. And then if I take the nth term and multiply it by r, then I have a times r to the n. Now I want to take a brief moment to remind you that in the past, you have taken two sets of equations with two variables, and I'm just going to say, for example, I'm just throwing these two out there. When you are looking for the intersection of two equations, you're looking for a place where both equations hold truth value. And when you are doing that, when you add the individual sides of the equation together, you get a new equation that holds the same truth value as the truth value of both of them. It stays in that realm. Do you remember that you would do things like, let's multiply by 2, and then when I add, I get 5x, and bye-bye equals 8 plus 10. And then all of a sudden you're like, oh, x is 18/5. Woohoo. So do you remember that you were allowed to do that? Okay. Then that's what we're going to do here. And I'm going to erase what I had written here so that you can see that what I'm doing is I am actually adding, no, not adding, subtracting the left side and the right side. When I subtract the left side, I have S sub n minus r times S sub n. On the right side, this loner a has no like term to add with. But this a times r minus this a times r is, come on, red pen. Rah! Gone. This a times r squared minus that a times r squared. Now, right after this plus sign, we know that the next term that was going to be written there was going to be an a times r cubed. That is going to cancel with the subtracting of a times r cubed. Then over here, we know, even though it's not written, that the term right before this one is a times r to the n minus 1. And that is going to cancel when I subtract this final term of s of n with the second to last term of the r times s sub n. And you should be able to see in there that those dot, dot, dots go, ah! And they're gone. And the only thing left is the first term of the initial s sub n series, and the last one of when I multiply by r. And it's subtracting. So this equation holds to be true. And then to get a formula for s sub n, I'm going to first factor s sub n from the left side. That will leave the left side as 1 minus r. On the right side, I have a minus a times r to the n. And then a little division later, okay, eraser, listen to me. There we go. A little division later, and I have a formula for the nth partial sum of any geometric series, whatever its r may be. With that, I can then take a look at what is the limit as n approaches infinity of that formula. If there is an answer to that limit, then I have a converging geometric series. But if this limit does not exist, then I have a diverging infinite geometric series. Now, it's going to take us a little bit of time if we want to genuinely look through all the cases of values of r. And let me remember, we are out of here at 12:50. Oh, I can get into some of these. Here we go. Let's start with if r is a number greater than 1. Now, earlier we took a look at that situation. Where'd it go? Oh, I went to the other class. I see. Oh, yeah, there we go. If you are dealing with an r that is greater than 1, then you are dealing with something that is matching the continuous graph, somebody who has its points on the continuous graph of exponential growth. And I'm not even going to bother mathematically showing you. You should be able to logically understand that there is no way you're going to get a converging series if you continue to create terms by multiplying by greater than 1. And I want to make sure, though, that you are clear through an example. And that would be if I have 6 plus. If my r is 2, then 12. And then times 2 again, times 2 again, times 2 again. Now, if I do this forever and then I add them all together, can you logically see there is no way this is unbounded? This is heading to infinity. And do you feel comfortable saying that if r is greater than 1, then you have a diverging geometric series? The next case that I want to look at is if r is between 0 and 1. And I'm going to turn to this limit. If r is between 0 and 1, can you tell me what the answer to this limit is? Oh, the question of where did I get the 6, 12, 24, I was showing an example of an r equals 2. This is an example series for an example geometric series where its r is 2. To show as an example, this is what it looks like when you have an r that's greater than 1. You are making numbers blow up. They're getting super big. And now I have the question, if r is a number between 0 and 1, what is going to be the limit as n approaches infinity of that number r to the power of n? Oh, I'm going to bring it back into the whole expression. I first want to just focus in right here. Just right here. If you have a number between 0 and 1, and you're looking at the limit as n approaches infinity, what I want you to recognize is that is looking at exponential decay and only the terms of the exponential decay. 1/2 to the n. If I am looking at 1/2 to the power of n, then these are the individual terms. The terms themselves, just r to the n by itself, do you see that the value is heading to 0? That is certainly not dealing with the entire partial sum. So I'm going to take that back to the formula that we do have for the nth partial sum, if I can figure out where I put it. There it is. Here's r to the n. If I'm dealing with r being between 0 and 1, now I can't find where I wrote that, so I'll just write it again. Do you see that the limit as n approaches infinity of this nth partial sum formula must be equal to a minus 0 over 1 minus r. In other words, if you know that your r is between 0 and 1, not only do you know that it converges, this is the formula for the infinite sum. And we're going to finalize that on Monday, but I want to talk through the various situations to make sure you are very, very clear as to why the geometric series only converges for certain r's. And there are other r's that we really don't bother with. Are we going to bother with r equals 0? If r is equal to 0, then the sum of the series is literally just the first term, provided that that's not 0. And if it is, then the sum is 0. Hey, do you recognize that bell? That bell says your class is over. So we're stopping right here, and understand that I realize many of you are feeling like that was a lot of information. I'm not used to dealing with sequences series. I'm going to go over what's important that we grabbed from today, and then continue on Monday and get you ready for a homework that you will have Monday. But it's time for you to go. So I will see you later. And I need to stop recording.
Thanks, Ms. Blanchard. Have a great weekend.
Thank you. You too. And come